everybody, and welcome to our first video in gas laws, which will be all about the kinetic molecular theory. The kinetic molecular theory, it sounds scary and it sounds like, oh my God, this theory of gases, what am I getting myself into? But these are all things that you already know for the most part. We're just kind of putting a name to all of these different ideas about gases that you already know, and just going slightly more in detail about certain things. And they explain why gases behave the way that they do, which is crucial when we talk about the gas laws, which is really the basis for this unit. So let's go ahead and start with just a definition. So the kinetic molecular theory of gases states that particles of matter are always in motion and can be used to explain the properties of gases in terms of the energy of particles and the forces that act between them. So gas particles behave in a very specific way, which is what gives them the properties that they have. And we can also talk about the energy that those particles have, and also the forces of attraction between the particles themselves. And of course, what we need to recognize is that gas particles are always moving. So if we look at this little image down here, you'll see that each one of these little circles is a gas particle or molecule, and every one is constantly moving. So that's what these arrows are representing, moving in all different types of directions. Now, the ones that you see kind of have a little, like they're going in one direction and they move another direction, that just means that they're bouncing off the container walls, which is something which we're going to talk about in a future video. But yeah, gas particles are always moving. Let's get into the 5 postulates. The first one states that gases consist of large numbers of tiny particles that are very far apart relative to their size. So if you consider a solid and a liquid versus a gas, solids and liquids are really compact together. I mean, there's barely any space in between these solid particles here, and there's only slightly bit more space in between the liquid particles. You can see there is a little bit more space in between them there. However, gases have significantly more space in between the particles. So if I look at this image of a gas right here, look how much space is in between each of those particles, as opposed to a liquid. Some of the liquid particles are still touching, and solids, they're basically all touching. So you can fit quite a bit more gas particles in between them. They're far apart considering how small that they are. I don't remember what reference or what resource I got this from, but I feel like I saw that gas particles are about 4,000 times farther apart from one another than they are from liquids. So that's a lot of space that's in between those particles. And they have to be far apart because they have that added rotational motion. Solids have vibrational energy. Liquids have vibrational and translational. That added rotational energy to gases makes them want to be very far apart from one another. And typically that happens with an increase in temperature. So we'll see here that as temperature increases, the amount of movement, the amount of energy that those atoms or molecules have also increases. But the amount of interactions that the particles have with one another is less. If I look here, this liquid particle is surrounded very closely with other liquid particles. Gases, not so much. Gas particles really don't interact with one another. They're far apart. The second postulate states that collisions between gas particles and between the particles and container walls are elastic. So if you have taken physics already, you might be familiar with the word elastic. But elastic means that there is no net loss of energy. So if you're considering velocities here, I have some particle with some mass, that's what M is, and I have another particle with another mass, and they're traveling at two different velocities. Notice how this one here has a little bit of a longer arrow, which we would assume is moving a little bit faster than this one right here. These two moving at different velocities collide. And when they collide, you'll notice that even though these two particles of different masses now are moving at two different velocities than what they already were, so this M1 is now moving slower, but this M2 is now moving faster, the net movement, the net velocity has not changed. If you were to add up the velocities of each of those before the collision and after the collision, they would be the same. So there is no net loss of energy. So we're going to click on this little image here just to see some elastic collisions in place. So we'll go ahead here, take a look at this. So here's an animation that you can, it's kind of hard to see because there's a lot of movement going on the screen, but shows elastic collisions very, very nicely. In this whole system, so a system is something where this is all within one. Consider this like one reaction vessel, one beaker with a lid on top, just one system, okay? There's no net loss of energy. So if you were to follow one of these atoms or molecules on the screen, they're colliding with one another. And as they collide with one another, they're exchanging energy in a way that this whole system is not losing energy. These particles are not just going to stop moving at some point in time. These will continue moving longer than all of us are going to be on the earth if these were truly elastic collisions. So even though one might be moving slow and then it starts moving really fast, that's because energy has transferred from one to another. And we call that an elastic collision. There is no net loss of energy. The third postulate states that gas particles are in constant rapid, random motion, and therefore they possess kinetic energy. So gas particles are always moving, right? They have that vibrational, translational, and that rotational energy. They are always moving very rapidly. So not only are they bouncing into one another, the gas particles, but they're also colliding with the container walls, which is what this is showing right here. So when it shows this change of direction, that only happens when it hits another particle or when it hits the wall, just like it is here. So this is hitting the container wall. This one's hitting the container wall, as is this third one over here. Fourth postulate states that there are no forces of attraction or repulsion between gas particles. Because gas particles are very far apart relative to their size, they're not close enough to want to attract one another if they're polar, or to repel one another if they're polar. The best example I can use to kind of demonstrate this is if you're playing pool. So when you play pool and you have that white cue ball and you break whatever that thing's called. I haven't played pool in a very long time. But when you break that set right here, when you break all of these, those balls move in any direction, not influenced by any other one. They're not attracted to one another and they're not repelled from one another. They just are. They just exist. They move in whatever direction they just happen to be moving in. And that's how gases work as well. They're not attracted to each other and they don't repel one another. They just are. And therefore they are constantly moving in some direction until they happen to hit one another, which will happen by chance, or they run into the container walls. The fifth postulate states that the average kinetic energy of gas particles depends on the temperature of that gas. That's what temperature is it's a measure of kinetic energy. So the higher the temperature of a sample of gas, the more those particles are moving. That's literally what a thermometer does, is it measures how much are the particles in your sample moving. So when I take a look at this image here on the left, this is going to be at a much lower temperature. And we know it's at a lower temperature because those particles have less kinetic energy. The only way you can kind of tell is that there's less like little swoopy things after this. That's just showing that these are moving more slowly compared to the ones on the right. So on the right, these ones have a very large little thing to show that they're moving more quickly. And in that case, these would have a much higher temperature and therefore have more kinetic energy. The higher the temperature of a sample of gas, the more kinetic energy that those particles have. So let's talk about the kinetic molecular theory and what that means about gases in themselves. So gases have an undefined shape because they don't attract or repel one another. They have a very high amount of that rotational energy, and they're very far apart relative to their size. They have an undefined shape. I can take a gas sample and put it in any container I want, and they will take the shape of that container. Gases are fluid, which is interesting. You normally think of only liquids as being fluid, but gases are fluid as well. And you can envision this by thinking about one of those cauldrons of dry ice around Halloween time. So dry ice, it's solid carbon dioxide, but it sublimes. So it goes straight from a solid to a gas. It skips the liquid phase entirely, which we're going to talk about in the next one maybe? I don't remember, but anyway, that gas actually falls down. Those particles could slide past one another, which means that they are in fact fluid just as liquids are. Liquid particles can move past each other, so can gases, and therefore gases are also considered fluid. Gases have a low density. Again, they're far apart relative to their size. The mass per unit volume will be very, very small. If I have a container full of gases or gas particles, because those gas particles are far apart, they're not as close to one another, and therefore the mass inside of that volume will be very low. Gases are compressible. Again, we could force the gas particles to become closer to one another by lowering the volume. And gases can diffuse. So over time, gases will move from an area of high density to an area of low density. So if you were to have these two samples here, so if I have hydrogen gas in one side of a vessel and I have nitrogen gas in another side of a vessel, and if you were to open this little valve in the middle, these two gases would spontaneously mix in a way where their concentrations are equal. You might remember talking about that in biology, AP biology, which I believe some of you are in or have taken before. But gases always, or anything really, wants to go from an area of high concentration to an area of low concentration. And that's true for gases as well. So I have a very high concentration here. This gas will diffuse to the other side to lower its concentration. And the same thing goes for hydrogen going through the valve into the other side until eventually their concentrations are the same. Something else we have to consider, so this is approaching that second learning goal, is the theory of an ideal gas. So we talked about all 5 of those postulates just now of the kinetic molecular theory. And that is true, or those 5 postulates are true for ideal gases. So an ideal gas is an imaginary gas that perfectly fits all of those postulates of the kinetic molecular theory of gases. So if you have a gas where the particles are far apart relative to their size, they don't attract or repel one another, whatever the other ones are, that's an ideal gas. However, most gases will not follow those 5 postulates, and we call those a real gas. A real gas does not behave according to the postulates of the kinetic molecular theory. So I always like to compare this to your ideal significant other and your real significant other. So when you start getting into the dating world and you're starting to look for somebody to spend your life with or whatever, you have all of these qualifications, right? They need to be really, really tall. They need to be really nice. They need to, like this type of music. They need this, and this. They have all these things, right? And then you start getting out there and you learn that nobody's gonna have all of those things that you're looking for. So maybe they have some of those qualities, but they're not going to have all of them. You have your ideal significant other that follows, that has all of those qualities you're looking for. And then you have your real significant other that doesn't have all of those, but they might have some. And gases are the same way. Ideal gases follow all of those 5 postulates perfectly, whereas real gases don't. They might follow 3 out of the 5, let's say. They might follow none out of the 5. So the question now is, if we have ideal gases and real gases, what makes an ideal gas behave real? What are the conditions that a gas will behave more real than ideal? And there's really 2 conditions, and they deal with temperature and pressure. So if we have these 2 systems at 2 different temperatures, so notice here, I have this temperature, or I have this gas at a very low temperature. And we'll learn about the gas laws, but because it's at a low temperature, the pressure is very high, whatever. In this case, I have a gas that is at a very high temperature, which we could tell just by looking at the thermometers, obviously. If we're considering the postulates of the kinetic molecular theory, which one of these does not follow all 5 postulates? Pause this video for a second, look at those postulates and see if you can determine which one of these beakers does not follow those postulates. Go ahead and pause this video right now. Hopefully you paused it and you tried to figure this out on your own. But this one here on the left does not behave like an ideal gas. This one will behave more real. And that's because at a low temperature, if you consider the first postulate, which says gases are far apart relative to their size, look at this. These gas particles are not nearly as far apart as they are for a gas that's at a very high temperature. So that first postulate is thrown out the window because gases at low temperature are very close to one another. So that's one reason, or one scenario, I should say, in which a gas will behave more real. Gases behave more real at low temperatures because they are very close to one another. Gases like to be very, very far apart like they are here. Gases at high temperature are preferred as opposed to low temperatures. Here's another one. So pressure is our second instance where a gas behaves more real or ideal. On the left, I have a gas that is at a very low pressure. And here I have a gas that is present at a very high pressure. So again, pause this video and see by looking at those postulates, which one of these would behave more real? Which one of these does not follow all 5 postulates of the kinetic molecular theory? You might be able to figure it out just by thinking about the last one. So go ahead and pause this video. Hopefully you did that. And if we look, okay, so this one here has a low pressure on the left. On the right, we have a high pressure. Gases behave more real at a high pressure. And again, that is because they are very close together relative to their size. You can also consider that if these particles are very close to one another, if they are polar molecules like water vapor, highly polar molecule. If you have water vapor And if it's at a very high pressure, if they're very close to one another, they could start to attract or repel one another. And that again gets tossed out the window. That postulate, I believe it's 4, maybe 3 or 4. I don't remember. You don't have to memorize what number they are, but just an idea of the postulates. So gases at high pressure behave more real than ideal, again, because they are very close to one another. And because they are so close, they could start to experience attractions or repulsions. So low pressure behaves more ideal. Here is just a general breakdown of gases that behave more ideal versus real. So gases behave ideal at high temperature and at low pressure. High temperature because they have a high kinetic energy, they are in constant rapid random motion. Low pressure because they are far apart relative to their size. Additionally, you have small non-polar gas molecules. Non-polar gas molecules tend to behave more ideal because they're not going to be attracted to one another. If I have like water vapor, for example, which is very polar, those water molecules can attract one another via hydrogen bonding, and that doesn't happen for an ideal gas. So non-polar gas molecules tend to behave more ideal, whereas polar gas molecules start to behave more real. So ones like ammonia, water, because they have the ability to hydrogen bonds to one another. Anything that's polar, hydrochloric acid, dipole, intermolecular forces of attraction, you're going to learn much more about in the next unit. They're polar, so they attract each other, which throws away one of those postulates. So here's a nice example of a gas being fluid. So here you have this gas that's starting to kind of come up of this vessel, and then it's falling. So this gas is in fact fluid, which again is not something you normally think of for gases, but it is true. Gases are fluid because the particles can move past one another. This whole section of this unit is much more conceptual than it is, doing calculations. I know it's very easy for you to just plug numbers into an equation and solve and get the number. This first part is not like that, but the kinetic molecular theory is very important, not just in this class, but if you decide to take AP, you will be required to know the kinetic molecular theory and also be able to differentiate between ideal gases versus real gases. We're going to get lots of practice in Chem 2 as well, but I just want to let you know that just because it's not mathematical doesn't mean that you're not required to know it. Anyway, I hope this helps. If you have any questions, please feel free to stop in and see me, whatever time works for you. Make any notes. If there was something you had a question on, make a little star, come by and ask me in class. Otherwise, I will see you in the next video, which we're going to start getting into the math all about the gas laws. So I will see you then. I hope you have a great day. Bye.